Hello, and again welcome to this presentation about heuristic partitioning of real-time tasks on multiprocessors. Nowadays we have more and more multiprocessor devices and more coming in the future, leading, for example, Android running smartphones, smartwatches. Users require interactive contents and applications demanding high quality and responsiveness, which leads to the needs for real-time capabilities of such systems. A fundamental problem in real-time scheduling is task partitioning, where we want to assign a new task to a core, while trying, for instance, to minimize the device consumption or having the best performance possible. But before to make a task on a core, it is important to have schedulability guarantee. Real-time tasks must be guaranteed to be given for enough time the CPU to complete within their deadline. To guarantee that each task completes within its deadline before being admitted on a core, they must pass an admission test. There are various admission tests, and they vary depending on whether it is a uniprocessor or a multiprocessor system and a used scheduler. If the new task passes the admission test, then it is admitted on a core, and all the tasks on that core complete within their own deadlines. So when it comes to real time, we have the fundamental problem of admitting tasks in the system. For uniprocessor systems, we have already a simple and effective test based on task utilization, while for multiprocessor devices, there is no such optimistic and easy-to-use test. And our solution tries to fill this gap with an heuristic admission test suitable for being applied online in real-world use cases and allowing to incrementally partition task sets. With respect to the state of the art, this admission test accepts more task sets under partitioned ETF by considering not only the heaviest task in the task set, but also the few k heaviest tasks. The problem of partitioning tasks is implicitly based on the bin pegging problems, where items must be allocated into bins such that the final bin weights are less or equal than 1 plus possibly other constraints. The bin pegging problem is known to be NP-hard, making other related problems intractable in polynomial terms as well, like also minimizing the energy consumption. However, there exist some efficient heuristics. Other partitioning techniques consist in splitting real-time tasks into two pieces that are allocated on two different cores. But here, the schedulability analysis and the admission tests are complex, making them not suitable for being applied online. Finally, some papers deal with the problem of adaptively partitioning task sets while minimizing the energy consumption, and they do it online. Some integer linear programming approaches exist as well, but they are applied offline, while we are interested in admission tests to be applied online. Then there is the utilization-based admission test that we used as a starting point for our approach, and it has the problem of considering only the heaviest task of the task set, while instead we consider the few k heaviest tasks and then make the OR with it. We will discuss in more detail about it in the next slide. Before moving to the heart of the conversation, in our system we consider n real-time tasks, and we suppose, for the sake of clarity, that they are ordered by utilization. Tasks are scheduled under partition EDF on an M-core symmetric multiprocessor platform, and tasks do not interact with each other. Now we present our solution. Our test is the combination of the basic admission test already proposed in the literature and one between a combinatorial or a linear test. In particular, the linear test is derived by the combinatorial one by exploiting some mathematical properties. The combination of the two tests is given by the OR, which means that a task set is admitted in the system if either test would admit it. The tests combination makes the admission test more robust, because it admits more task sets than the two parts would do alone. The basic admission test works on tasks utilization and checks only the heaviest task of the task set, while our test returns and compares the maximum number of tasks that can be admitted in the system and checks the few heaviest tasks. We now give an intuition of the two approaches, the utilization-based test first and then ours. Keep in mind that the final admission test that we propose is a combination of the two. For the utilization-based test, consider the task sets in the slide composed of 6 tasks with total utilization 2.6. The state-of-the-art approach takes the task set and computes the maximum utilization that can be handled with the formula that you see in yellow. Then, if the task set total utilization is less than the results of the formula, then the task set is admitted and scheduled. The formula only takes into account the heaviest task with utilization U1 and the number of cores M. In the example, the task set total utilization is 2.6 and it is not less or equal than the result of the formula, and so the task set is not admitted in the system. Our approach instead will accept the task set. We must explore all the possible ways that the k heaviest tasks can be deployed on the cores. If k is equal to 3, we must see how the first 2 tasks can be placed on 2 cores. With k equal to 4, as in the bottom part of the figure, we must see all the 3 tasks on a core, all tasks separated, and all the possible remaining configurations. And as you can see, it is a combinatorial approach, but we also developed a linear variant, which is of course simplified and does not accept some task sets the combinatorial one admits, but it is also faster. So in general, we have to explore all the possible ways to partition the k heaviest k-1 tasks on k-1 CPUs, which makes the approach combinatorial. Then we can compute the number of tasks that are admissible. We pick the minimum, and we decide whether to admit or not the task set. Given the combinatorial approach, the first fit is not mandatory here, while instead in the state-of-the-art approach, it is. Let's see our method being applied. It takes into account the few k heaviest tasks in the task sets and returns the maximum number of tasks that can be admitted in the system. By changing the number of heaviest tasks that are considered, its precision increases, and the number of admitted task sets grows. By doing so, it admits task sets that the state-of-the-art approach does not admit in the system. If k is equal to 3, our approach will accept up to 6 tasks, and this task set contains 6 tasks. Thus, the task set is admitted, while the state-of-the-art approach rejects it. If we decrease the number of heaviest tasks taken into account, the test becomes more pessimistic, which means it accepts fewer task sets while getting computationally faster. If we consider only the heaviest task, so only one, the heaviest, the number of admitted task sets decreases. That's the reason why in our test we consider the few heaviest tasks and not only the heaviest one. However, the choice of the number of heaviest tasks to be considered is key to have a good balance between performance and effectiveness of the algorithm. We propose 2 basic admission tests, basic because at the end we consider the OR. The combinatorial test accepts more task sets, but it has a higher complexity. The linear test instead is a derivation of the first one via some mathematical properties, and it accepts less task sets. But in many cases, it is better than the state-of-the-art approach alone. It has a linear complexity, but it can be reduced with some smart implementation, and thus it is suitable for real-world admission tests that work online. Both the basic tests that we propose consider the first k heaviest tasks, and if you increase k, you get more task sets accepted. Both tests return a number and work with partition EDF. Moreover, they allow incremental task set admission tests, which means you don't have to give task sets by the beginning, but you can give them incrementally. We now discuss about the results of the experiments. The graphs show on the x-axis the number of tasks in each task set, and on the y-axis the number of admitted ones. As you can see, the state-of-the-art approach admits all task sets in many cases, but already with total utilization 2.6, it falls down to 0, as indicated by the red arrow. Instead, our tests continue admitting task sets in the system. Already when only considering the 3 heaviest tasks in the task sets, the combinatorial and the linear tests show better results than the state-of-the-art method, as in the orange and red bins. Also, the combinatorial test is computationally heavier but also more efficient than its corresponding linear test. In fact, you can see in the figure that the red bins are always higher than the orange ones. In this graph, the yellow arrow shows that the combinatorial and the linear tests dominate on the utilization tests, which is the one already proposed in the literature, starting from system utilization 2.6. We now consider a greater number of heaviest tasks for our 2 tests. As you can see, the combinatorial test that takes into account a greater number of heaviest tasks, in this case 4, as in the dark blue bins, is always better than the one taking into account less of them, in this case 3, as in the red bins. The same fact applies for the linear test for different values of k, so that the light blue bins are always higher than the orange ones. However, our final admission test is the combination of the state-of-the-art method and either the combinatorial or the linear test. This is represented by the white and black bins, which report higher numbers than the basic tests. And as you can see, already for k equal 4, the number of accepted task sets increases significantly for total utilization greater than 2.6. White bin's length is the maximum between the results of the state-of-the-art approach in yellow and the combinatorial test for k equal 4 in this case. Similarly for the black bins, where the maximum is between the yellow bins and the light blue bins. Take the total utilization 2.6. The yellow bins, which is the number of task sets admitted by the utilization-based test, is 0, while the dark blue bins, representing the combinatorial test for k equal 4, is much higher. Thus, the white bins report the value of the maximum, which is the combinatorial test, the dark blue bins. Now we change only the number of tasks in each task set generated randomly. As you can see, the basic tests taken alone show different behaviors than before, since the state-of-the-art approach is now more effective than ours. In fact, their behaviors depend on the number of cores, the number of heaviest tasks considered, and the number of tasks in each task set. However, the joint admission test is still robust, already with k equal 4, as the white and black bins show. For the case of 4 cores, our tests show its strengths when used in couple with the basic test, which make the combination of the admission tests more robust since more task sets are admitted. Notice that not always one test dominates the other one. Concluding, we presented an admission test for symmetric multiprocessor platforms under partition EDF. It is a fast test that is suitable for being applied online in real-world admission tests, and that increases the number of admitted task sets in the system. It is based on the combination of two separated admission tests, and our experiments show that the tests combination introduces the robustness in the final admission test, and then its performance may be even better with different benchmarks and with different kind of task sets. So the key points for these new admission tests are to take into account more heaviest tasks and not only the heaviest one, and to combine simpler tests to have a more robust one. As for the future works, we plan to extend to non-symmetric platforms such as the ARM-Big-Little and to SMP platforms with dynamic voltage frequency scaling capabilities. And thank you for your attention.